Hi, I'm Tim, and this is video number 9 in the series about antigravity matter. This one gives an overview of how antigravity matter affects the Galaxy Lifecycle. I'm going to be using a lot of technical terms and concepts without explaining them in this video. If you haven't already, please see the other videos in the overview series linked to the website. Before we get into the Galaxy Lifecycle, I want to emphasize a few points from the preceding videos. Stars produce a lot of gas and dust, particularly at the end of their lives. The gas and dust collects to form molecular clouds, and molecular clouds cool and collapse to form new stars. But the formation of what we would recognize as molecular clouds only happens in the presence of a cool antigravity matter atmosphere. By cool, I mean a few thousand degrees or less. If there's no antigravity matter atmosphere, or if the local antigravity matter atmosphere is too hot, molecular clouds don't form. The dust and gas stays spread out and stays hot. That means that new stars also don't form. There are two reasonably stable behaviours of stars in a star group. The first is chaotic. That is, stars are falling in towards the centre, interacting with each other chaotically, and flying outwards again. A star group like this is spherical, not elliptical, and it doesn't rotate. In the core, the stars have reached their AGM exclusion density, and a shared AGM boundary has formed around the core. There's no antigravity matter inside the shared AGM boundary. The stars there are in an AGM excluded state and are not affected by AGM drag. Outside the core, stars are pushing through the antigravity matter atmosphere and are affected by AGM drag. They each have AGM boundaries of their own. The stars outside the core are in an AGM mixed state, which gives the group a diffuse appearance. The apparent gravitational attraction of the group is increased by the static AGM lacunas of the stars and of the inner core. It is approximately doubled. A star group like this does not form recognizable molecular clouds. That's because there's no antigravity matter in the core, and because the stars outside the core are still densely packed and moving chaotically. They stir and warm the antigravity matter, and they stir the gas and dust. That prevents molecular clouds forming, and it prevents new stars forming. There's plenty of gas and dust in interstellar space, but it just remains spread out and mixed with the antigravity matter atmosphere. There might be an antigravity matter wind blowing past the star group. If so, it blows between the stars outside the core and blows the interstellar gas and dust out of the group. The gas and dust can then collect and create molecular clouds and new stars, and these sometimes show up as a drag tail of new stars behind a star group. Pulsars don't get kicked from inside the core because there's no antigravity matter there to kick them. Chaotic star groups lose energy steadily to AGM drag, but star movement can be re-energized by interaction with objects outside the group or by the stirring motion of black holes forming and merging in the center. The second type of star group is a rotating disk. The stars in the disk are mostly in an AGM mixed state. There is antigravity matter in interstellar space. The rotating disk drives an AGM vortex which generates a dynamic AGM lacuna which extends away from the disk and gives the impression of a dark matter halo. Outside the disk, it generates an antihalo. The effect of static and dynamic lacunas can be to multiply the gravitational attraction of the normal matter in the group by several times. The antigravity matter wind blows outwards in the disk. Molecular clouds form and are carried outwards. They form new stars in the outer reaches of the disk. The molecular clouds are not on a circular trajectory, so when new stars form, they are often in non-circular orbits, but their orbits become more circular as they decay and migrate inwards. Rotating disk star groups also lose energy steadily to AGM drag. In this video, I use the term elliptical galaxy to mean only galaxies of the first type with chaotic flow and spherical shape. It can get confusing, and sometimes people use the term to mean objects that look elliptical from Earth even though those objects may be actually rotating disks viewed at an angle. There are two types of spiral arm. Tidal spirals are caused by the tidal disruption of usually two preceding galaxies. AGM drag spirals are caused by AGM drag effects as the antigravity matter flows outwards through a rotating disk. But the AGM drag spiral mechanism doesn't work if the antigravity matter atmosphere is too hot. If the AGM drag spiral mechanism doesn't work, a rotating disk can be fairly featureless. So now we're on to the Galaxy Lifecycle, and it forms a circle. I'm going to describe it starting with an elliptical galaxy, because as you'll see, it ends with an elliptical galaxy. Remember, elliptical means spherical object, chaotic star flow, no rotation, no internal molecular clouds, no pulsar kicks, and no star formation. The stars in an elliptical galaxy can be very old. The galaxy starts to interact with another galaxy. They orbit each other and start to generate an AGM vortex. This generates a dynamic AGM lacuna, which increases the attraction to the centre of the system, which increases the rate of rotation. The two galaxies are disrupted by tidal effects. They are stretched out and become tidal spiral arms. The arms push through the antigravity matter as they rotate. The stars which were outside the two original galaxy cores are affected by AGM drag. Their orbits decay faster and they move forward along the spiral arms to the front. The AGM vortex is driven by the two spiral arms. There isn't much mass in the central region. That means that the dynamic AGM lacuna is flat-bottomed in the central region. That means that orbital velocity is proportional to radius in the central region. As those stars' orbits decay, they enter the central region and form a galaxy bar. They remain AGM mixed, and the galaxy bar has a diffuse texture. The outer tidal arms are the remains of the dense inner cores of the two original galaxies. The stars there are still mostly AGM excluded. The arms are bright and dense. As they are stretched, they break up unevenly, and the arm gets a globular texture. Stars escape from the AGM exclusion regions, and they're slowly eroded. Dust and gas from the preceding galaxies also escapes and forms molecular clouds. Some of these migrate forward and fall into the galaxy bar. Others find shelter from the AGM wind behind the AGM excluded star groups. Others are blown into the space around the new galaxy. As time passes, the mass in the centre increases and the AGM vortex is driven more from there. The AGM vortex loses its flat bottom and the galaxy loses its bar. The two preceding galaxies break up to form the rotating disk of the new galaxy. The rotating disk has the form previously described. The last remaining fragments of the old AGM-excluded inner cores become globular clusters in the new galaxy. Star behaviour within the globular clusters is chaotic, also as previously described. Globular clusters contain old stars from the previous galaxy cores, but they are temporary features in the new galaxy. AGM drag spirals form in the disk, and the orbits of stars in the disk continue to decay. The galaxy becomes denser in the centre. Eventually, the central region gets to its AGM exclusion density, and a shared AGM boundary forms around the inner core. The behaviour of the stars in the inner core becomes chaotic, as previously described. More stars fall into the inner core and deliver kinetic energy and angular momentum. Stars are ejected from the inner core into the outer core, where they lose energy and angular momentum to AGM drag. Most of them fall back in again. The galaxy now has a central bulge. The disk continues to fall into the core. Most globular clusters have decayed away. There's less mass in the disk, so the AGM vortex reduces in intensity and the dynamic AGM lacuna reduces in depth. The difference in velocity between the remaining stars in the disk and the antigravity matter atmosphere reduces, and the drag spiral effect reduces. The disk becomes more featureless. As the last remnants of the disk fall into the core, the galaxy takes on a lenticular shape before it eventually becomes an elliptical galaxy and the circle is complete. Star formation stops in the new elliptical galaxy. It now contains stars from each of the 2 preceding galaxies, and it contains new stars that were formed during its period as a spiral galaxy. If we analyse an elliptical galaxy and find it contains stars in discrete age ranges, that means that those were the ages when that elliptical galaxy, or its ancestor galaxies, were going through this spiral galaxy process. This is the main process for building elliptical galaxies. Stars are lowered slowly into the new galaxy by the spiral galaxy process. In isolation, an elliptical galaxy may even slowly lose mass by evaporation and by the AGM wind blowing its interstellar gas and dust away. Of course, the process I've described is rather idealised. When it comes to real galaxy collisions, there are infinite variations on the process. One important variation is when it takes place within a galaxy cluster. Within a galaxy cluster, the antigravity matter atmosphere can be very hot. That means that it's more difficult for molecular clouds to form and for new stars to form. Gas and dust just stays spread out within the cluster. It also means that the drag spiral mechanism has less effect and galaxy disks can be more featureless. And here's an example of that. This is a spiral galaxy with no spirals and no star formation. That's because it's in a galaxy cluster. For more information on that one, see the video on NGC 1277. So that's it, a complex process that explains many of the observed features of galaxies. I'm going to leave you with a list of some of them. Again, if you haven't already, I recommend you view the other videos in the series to get a more detailed explanation.